Hello and welcome back. This is going to be part 2 of our chapter 13, Analysis of Variance, or ANOVA. So one way, analysis of variance or ANOVA. What it is we're going to take categorical explanatory variables and quantitative response variables. Remember back to our PET where we had whether or not they had a dog, a friend, or neither. These would be placed in categorical variables, and then we had a quantitative response in their heart rate. What we're going to do next is test the group means for a significant difference. So the way we set this up is instead of running multiple t-tests, we're going to run analysis of variance because we have over 2 groups. So we're going to state our statistical hypothesis. For our statistical hypothesis for ANOVA, it's going to be, remember, a null hypothesis is a statement of no difference. So we're going to have group 1 equaling group 2 equaling all the way up to group K. We use subscript K to symbolize how many groups there are. The alternative hypothesis is at least one of the groups is going to differ. We might not know exactly which group differs, especially if we're running, 4, 5, 6 groups. We might not know which group differs, but ANOVA will tell us if there is a difference. So our alternative hypothesis is that one of the groups differ. We might not know exactly which group, and that's where we do a post hoc testing afterwards. However, our alternative hypothesis is at least one group is different. Remember, our hypothesis statement has to be a null hypothesis of stating no difference, and our alternative hypothesis has to be the exact opposite, stating that there is a difference at least one group or more. So our method is we compare the variability between groups to the variability within the groups, and we get an F statistic. So what we have is our F stat is equal to our MSB over MSW. And this is going to be the difference between the groups and the difference within the groups. Our means between the groups and our means within the groups. This might sound confusing, and we're going to go over it in the next couple of slides. But this is the formula we use to calculate our F statistic. So our variability between groups. The variability of group means around the grand mean provides a signal of group difference. This is based on a statistic called the mean squared between. So here's our MSB, mean squared between. So we have a couple of notations here. Some of these you've seen before, SS, sum of squares with a subscript B for between. Our degrees of freedom with subscript B for between, degrees of freedom between. K is the number of groups. Our X bar is the grand mean, and our X bar I the mean of group I, or whatever group we are measuring. And what this is doing is it's measuring the mean squared between the groups. Mean squared between formulas. So once again, we just went over the notations here of SS subscript B, DF subscript B, K, X bar, XI. The formulas associated for mean squared between formulas are SS subscript B, or sum of squares between groups, is equal to K, which is the number of groups, the sum of I equaling 1, and then the number of the participant multiplied by the quantity of xi, the actual value of that, minus x bar squared. So this should look very similar to how we almost calculate standard deviation, minus a couple steps, but we're figuring out the sum of squares. As you remember, sum of squares is part of standard deviation. This is the formula that we set up exactly for this. Degrees of freedom between, degrees of freedom, df, subscript capital B, equals k minus 1, remember k being the number of groups. K minus 1 will give you degrees of freedom from between. And then our mean squared between, our MSB, is going to equal our k group sum of I equaling 1, multiply ni over xi1, or xi minus x bar squared. So as you can see, our MSB is taking the sum of squares divided by our degrees of freedom between. Sum of squares between divided by our degrees of freedom between. We calculate this and we get our MSB. And this is the numerator part for our F statistic. And this is measuring the variability between the groups. So this is measuring between the dog and the human friend and the test subject that had neither. This is illustrative example of it. So as you can see, this dotted line here is our grand mean, or the overall mean for the group, being 82.444. And this is where each group, so group 1, group 2, and group 3, where they measured in comparison to the grand mean, right? So this is the deviation between each of these groups. So now we're going to go to the mean squared between example. So if we go back to our data that we had earlier, that's number of groups, data earlier, here it is, where we had 15 people in each group. We had our x bar for each group, the mean for each group, and the standard deviation for each group, and then the total between. What we're going to do is we're going to take our x bar minus our x and put it into our formula down below. So you can see this. I'll scroll back down. For our sum of squares between. So what we do is we take our 15 multiplied by the mean of group 1 subtracted from the overall mean squared, and then 1 plus 15. I don't think that 1 should be there. I don't know how that typo got in there. And then it's plus 15, which is the number of group size, the mean of group 2 minus the overall mean squared, plus 15 times group 2 minus, or group 3 minus the mean squared. And when we put that in, we get a grand total of the sum of squares between being 2,387.671. Our degrees of freedom between, remember that was k minus 1. K is the number of groups, 3 minus 1 equaling 2. So now to get our mean squared between, our MSB, we take our 2,387.671 divided by 2, and we get 1,193.836. And that is how you calculate the mean squared between. So now we're going to start looking at the variability within the group. So before we were measuring the difference between each group, now we're measuring within each group the variability within the group. So it's a variability of data points within groups, and it quantifies random noise based on the statistic called the mean squared within. So mean squared within, so within each group. Here are notations for within. You'll notice they're set up the same, but with a subscript W for sum of squares within, degrees of freedom within, n being the sample size of all groups combined, and I is the sample size of group I, and S squared I is the variance of the group. So our mean squared within formula. So in order to calculate our mean squared within, it's going to equal the sum of squares within divided by degrees of freedom within. Much similar to how we were doing the mean squares between is the mean squares within. Here are the formulas for the sum of squares within and the degrees of freedom within. So once again, since we're measuring each group and the variability within each group, this is a visual representative of each group. So as you can see, here's pets, friends, and neither. The middle marker being the average point within each group and where the data points lie in comparison to the average. So now we go to our mean squared within example. So we have our sum of squares within, which is 15 minus 1, or if we go back up to our sum of squares formula within, we're going to have our n minus 1, so number of participants in the group minus 1, multiplied by our sum of squares of that group. So 15 minus 1 times the sum of squares in that group, not sum of squares, the variance, s squared, the variance of the group. So 15 minus 1 times the variance of that group squared, plus 15 minus 1 the variance group 2 and group 3. And when we put all that together and calculate it out, we have 3,561.316. So our degrees of freedom within, member, is going to be our n minus k, as you can see here, n minus k. So the total number of participants in the group. So we had 3 groups at 15. 15 times 3 is 45. Minus k, which is the number of groups. So this is where we get our 45 minus 3 equals 42. And that's our degrees of freedom within the group. So now when we want to calculate the mean squared within, we take our sum of squares within divided by our degrees of freedom within to get our mean squares within. So 3,561.316 divided by 42 equals 43.793. So now, taking all that information that we just calculated, so we just calculated the sum of squares between and, or not sum of squares, the mean squared between and the mean squares within, and then we calculate our F statistic now. So our F stat, remember, is equal to the MSB over MSW. When we calculate these out, we add these numbers, and then when we divide these out, we get an F stat of 14. And this is called the signal to noise ratio. It's called our F stat, signal to noise ratio. Now with the F stat, just like when we had a Z stat or a T stat, this is telling us where we can, how significant these groups are. As you can guess, an F stat of 14 is fairly large, and with this we have a whole new table with our F stat and p-value. So the F stat has a numerator and denominator degrees of freedom, represented by df1 and df2 respectively, corresponding to degrees of freedom between and then degrees of freedom within. One way to remember this is alphabetical order. B comes before W in the alphabet, and you're always going to correspond the degrees of freedom 1, degrees of freedom 2 respectively as degrees of freedoms between and then degrees of freedom within. So if you see something, degrees of freedom, a number for 1 and then a number for 2, it's always between them within when it comes to the F stat. You're going to convert the F stat to a p-value with a computer program or table D. Remember, we can convert with a computer program and get a very accurate number. If we go to our new table in the back of the book, so after table C here, when we were doing our t-test, we have a new cool table, also sideways, and it's table D, and it's entries for F values with a right tail probability. So once again, if you look in the back of your book, the way this table is set up is you have a degrees of freedom in the numerator, or df1, and then on the side you have degrees of freedom in denominator. So we know the degrees of freedom 1 is also corresponding to the degrees of freedom between that we calculate, and then on the left hand side, degrees of freedom on the denominator, or the degrees of freedom 2, is going to correspond to the degree of freedoms within. So that's how we look at knowing which degrees of freedom to look at for each group. Once again, the table is only going to tell us the critical values of F for these. So if our F value when looking this up is higher than the value shown, we can state that we have significance. If it's not, then there's not going to be significance for that particular statistic we're running. It's going to be hard to calculate a true exact p-value if it's in between. Remember, these are just showing us the critical points that if an F value or F stat is higher than this, then it is significant past that point, but underneath that point, it wouldn't be significant. The only way to actually find the true p-value is to run the statistical software, either SPSS or SAS or an R program, or you can even use Excel to some degree. This is where Excel starts getting a little tapered off, but it can still run simple ANOVAs, and you have to run extra things to get more out of it versus an SPSS. So if you go to table D in our F table, remember the F table has limited listings for degrees of freedom too. We can't list everything because there can be hundreds and thousands of them. So we do our best to have as many in there as possible, but after the degrees of freedom 2 on the left hand side, you notice after we get to 30, it jumps. It goes from or after 20, it goes from 20 to 30 to 50, 100, 1,000. Before that, it does have the degrees of freedom all within there. So if we were to look up what we just did for our F stat, With our FSTAT, you often must round down to the next available degrees of freedom 2. Rounding down is preferable for a conservative estimate. Remember, we always want to be as conservative as possible in statistics. So we wedge the FSTAT between the listings to find the approximate p-value. Once again, it's just an approximate. So we look up our degrees of freedom 1, which is equal to 2, and a degree of freedom 2, which is equal to 42. Remember, that's the degrees of freedom between and within. First one's always going to be between, so degrees of freedom 1 is going to be the degrees of freedom between, and degrees of freedom 2 is going to be degrees of freedom within. Table doesn't have an exact value of 42, so we go to our next lotus and go to 30. So if you were to go to the table, which will be found on page 553, you'll notice on the left-hand side, the degrees of freedom in denominator, you see the 30, and that's what we're looking for. And then we go to our degrees of freedom between, which was 2. So you go over to the column at the very top, it says degrees in numerator, find 2, go down to where the 30 meets. Now we have to find out where the probability matches up. And if you look at the table, or look here on the screen, you see an FSTAT of 14.02 falls below the p-value of 0.001. So if you look, here's our p-value at 10%, 5%, 2.5, 1, and 1 was 10, 100, thousands, so less than 1%. At the degrees of freedom, degrees of freedom 1 equaling 2, we had a 8.77 critical value for our FSTAT. So FSTAT 14 is well past that, so we know that the probability is quite high. An illustrated example of this would be, here's our curve coming down, and our FSTAT is over here at 14.5, and it's the area under the curve. So area under the curve to be 0.05, or a p-value of 0.05 being here, an FSTAT would have to be just at 3.32. For a 1% or a p-value of 0.01, 5.38 is the critical value. For a 0.001, 8.77. So our FSTAT is way out here. So we have a probability of less than 0.001. Once again, we can't calculate the exact one. We're just listing the critical cutoff value. And then we could state that our F value of 14.08 is highly significant. So here's an ANOVA example, or a summary of what we just did. So we had our null hypothesis, a statement of no difference, where mu 1, 2, and 3 are all equal to each other, versus an alternative hypothesis, where at least one of the mu's differ. We got an F statistic of 14.08 with 2 and 42 degrees of freedom. Remember, that's between, then within. And we had a p-value, when you actually calculate out, of 0.00021 via SPSS, or providing highly significant evidence against the null, concluding the heart rates as an indicator of effective stress differed in the groups. So, and we could say it's definitely statistically significant at this alpha level. Once again, when we ran our ANOVA tests, we got a very high F value, stating there is a difference between the groups. We just don't know where that difference truly is. We don't know if it's between group 1 and group 3, or group 2 and group 3, or 1 and 3. We don't know exactly where it states. It's just there is a difference there. So here's, if you were to use ANOVA in SPSS, this is what a chart would pop out and look like, and this is what you would get after running the test, and it would give you your between groups, within groups totals, your sum of squares, your degrees of freedom, all within your mean squares, your F certificate, and the significance, or the p-value associated with it. And this is what this will look like. Due to time, I'm going to end the video here, and I'll start the next one and show you how to run it in Excel, and then we will go on with the remaining of the chapter. Remember, the only thing I'm looking at here is calculating an F statistic. After that, I am going to post the videos about the rest of the chapter, but it's more just going to be theory and concepts going on. There's a lot more statistics that are going to be presented, but we're not going to be actually doing any of those statistics by hand. But it's very, I think it's very important to understand the next important step. So the next step after this is we have, like I said, a difference within the groups, but we don't know where. So this is where we go and do a post hoc test. And this is where we find out where there actually is a difference between the groups, what groups actually differ from each other. And that's the next kind of logical step in this thing. But we're not going to actually do those. These are, once again, just for concept and theory purposes. And I will see you in the next video.